Hey, how's it going, everybody? Today we have a very good problem that I'm pretty excited to show to you guys, right? So it's called check completeness of a binary tree. Let's quickly go ahead and read the problem statement, guys, right? So it says, given the root of a binary tree, determine if it is a complete binary tree, right? It says in a complete binary tree, every level except possibly the last, right, is completely filled, and all of the nodes in the last level it asks for levels possible. You can have between 1 and 2 to the h nodes inclusive at the last level, right? So this is a very good description, right? They've given us uh, the definition of complete binary tree, right? We don't need to remember that. And the clear, concise description, right? Like that. So we see that they're saying, guys, right, that for a tree to be considered a complete boundary tree, right, every level needs to be filled up, right, except possibly the last one, right? But the last level needs to be, although the nodes at present needs to be as far level as possible, right? So see the example. The example is going to make a lot clearer to us, right? So we see that all the levels are filled up, right, except the last, but uh, the nodes are as far level as possible, which makes this still considered a no, a complete binary tree, guys. Very important. That's good. This one is a little bit different, right? All the rows are filled up except the last, but the last one, right? We see that now all of the nodes are as far left as possible. We see that we encounter a null node there, right? And we see 7 there, but 7 is not far left as possible, which means this is not considered a complete uh, binary tree, guys, right? So this is very important. It's not complete based on the definition requirement, right? It needed to be, if 7 was to the left of 3, right, then we know that it would have been a complete um, binary tree, right? It would have been right in the same case as above, right? See the good way that they're showing us a different way, right? So yeah, because the rule is that it needs to be as full as possible. So how can we go about this, guy, right? 7 is not considered. 7 is after a null node, right? Which is not good. We can't have that, right? It needs to be straight filled up, right? And then we could have we could have nulls after that. It doesn't matter. Right? Nulls could exist after the last node, right? It doesn't matter. That's still fair game, right? At the last level, though, right? So that's fair game. Okay. We can have the case that say 3 wasn't there, right? And let's say 6 was there, right? But there's nothing to the right side of 1. It would not have been good, guys. It would have been not a complete binary tree because 1 would have been empty, right? Which is we can't have that case, which is not good at all. Okay, because he says every node, every level needs to be filled up, and then every node, the last level to the left as possible, right? If it's not completely filled up, right? Okay, so how can we go about this, guys? We know that we need to do some kind of traversal, right? And we need to, as we're traversing, make sure that the binary tree does it break the rules of the requirements, right, for it to be considered a complete binary tree or not, right? So that's why we need to make sure that we validate that as we're doing it, guys, right? Which is important, okay? So, can we, what kind of triggers will be better? DFS, BFS, level ordering, it's gonna be better. I think that the BFS level ordering, right, is gonna be better for this problem because we need to validate every level, and as we're going through every level, we could uh, also trying to make sure that all of the nodes are as far left as possible. Okay, but how can we do it though? How can this be applied here? Okay, how's it traversing in that manner be able to help us in this solve this particular problem, guys? Right? I mean, we need to see, is it obvious? Let me see. We can go from, so level traversal, right, go from top to bottom, right, and from left to right, right? As we're doing that, right, we can make sure that we maybe somehow can see if we've seen a null node before, right? Because if we can't have any gaps at all, right? See, this one we had a gap, right, which caused it not to be a complete binary tree, right? If there's a gap. If there's a null node, right, there should not be anything after that null node, right, in the traversal, right? So the level order traversal is gonna help us in visiting level by level, right? So we see 1, 2, 4, 5, 6, right? And then null could be fine, right? But we can't have the case where we see 1, 2, 3, 4, 5 null, and we see another node that's not null. That's not possible. We cannot have any non-null nodes after a null node, right? Because we can't have any gaps, right? For it to be considered a complete boundary tree, right? There cannot be any gap, right? And the thing about it is that we visit things level by level, which means we take care of every level, right? So we validate this level, it's good. And then we validate the next level, right? We're making sure every level doesn't break the rules, right? Right. So we cannot have the fact. So as soon as we find a level that breaks the rule, right, we automatically return, say, hey, this is not a complete binary tree, right? Because we saw something, right? And if we end up visiting the whole tree, right, and we then breaking the rules, right, we return at the end that this is a good binary tree, complete binary tree, and we return true, guys, right? So this is how we're gonna do it. We're gonna have a flag helping us know when once we encounter a null node, right? And then we know that we cannot encounter any non-null nodes, which means valid nodes, right? Not encounter any non-null nodes. If we do encounter any non-null nodes, right, it just means that it's not a complete one, right? Either that the nodes are not as far left as possible, or yeah, they're not as far left as possible. Okay, it needs to be, right? So I give you guys the case if 3 wasn't there, right? 3 was null, right? 6 was somewhere here. It still would have not been good because we would add 2 would add of each child, right? And then 1 would add null, right? Because 1 would be pointed to null, right? And then we would have the flag set to true, right? We've seen a null node, okay? That means that it, there cannot be any more node at the next level, guys, right? Because we've seen a null node at the previous level, right? And then once we see other nodes there, still we say, all right, cool, this is not a complete binary tree because it's not complete, right? All the levels needs to be filled up except possibly the last one, right? There cannot the next level cannot have more. I'm saying cannot have any more child if one of the nodes in the previous level was null, right? So this is what the point I'm trying to make clear to you guys, right? So if you the case, right? So in our traversal, we encounter any null nodes, right? There cannot be any null nodes, right? So yeah. So let's quickly go ahead with that. I've stressed it enough to you guys, right? Okay. So it should be no gaps, right? That's what I'm saying. So rank lists. We're gonna do we're gonna do a reference search, like we said, and we're gonna add the root to our queue, and then we're gonna do a while loop. Then we do our reference search while the queue, and see what we're gonna do. We're gonna get the size of the level, okay? Okay. What's next first is to loop through all the nodes for that particular level. So let me make sure I have enough space for you guys to see everything. So we loop through all the other nodes, guys, right? While the it's not so well, we're gonna do all the nodes, right? So we're gonna get 3 nodes, we're gonna get 1 node outside out of the queue, right? So we get the node out of the queue. So what we need to do, guys, remember I told you guys we need some kind of a flag to let us know if we've seen a non-null, if we've seen a null node before, right? So seen null node. Okay. So we initially is gonna be false. Okay. And yeah, so what we're gonna see if the node is null. Then we're gonna mark it, guys. Right? We're gonna mark this variable as true. Let's flag as true because we've seen a null node, right? Which is make sure that we're in the same page, right? And then if that's not the case, right? If it's not null, then we're gonna hit this else statement, which is going to help us adding the node in the queue, right? To visit there, right? So add node left. Okay. And then we add node right. Okay. So we're adding our children to the queue, right? So this is what we're doing here. So normally we should be in good shape, right? But we need to do another check here, guys, right? So before we add them to the queue, right? So if we before add our children to the queue, if the node, right? If seen, I mean, sorry about that, guys. So if we've seen a null node before, right, and we continue, right, and we see, so this one once we get to this node right there, right, this node, right, this would have been set to true, right? We set the null node to true, right? And then in the next iteration, we see 7, right? But we've already seen a null node, right? So we return false here, guys. So we've broken the requirements for it to be considered a complete boundary tree, right? So we visit everything, we're in good shape, we return true. Looks good to me. Let's press run code, see if we miss anything. No, that was a little bit slow. Let's press submit, we pass all the test cases. Awesome, guys. We were able to pass all the test cases, guys. So I want to thank you guys for taking the time to kind of watch this video, guys. If you guys found value, make sure to give me a like. If you guys are new here, make sure to subscribe because I'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.